Okay, so welcome everybody to this week's Majorana-Raychaudhuri seminar series. Today's first speaker is Stefano Profumo from University California, Santa Cruz, and he is going to talk about black holes as dark matter. And I'll send you a reminder when 5 minutes are left.
Thank you very much, Yanish. So, well, let's get this going. Thank you for having me. It's a privilege to be
मैं पहले
here.
टॉक सुनूंगी फिर बर्तन वर्तन बात
Somebody should probably mute themselves. We have a picture of galaxies, including our own Milky Way, which is one where the luminous matter, the stuff that we observe and know and love, is embedded in large halos of dark matter. On a global scale, there is very strong evidence, in fact, conclusive evidence, that 5/6 of the matter in the universe, the non-relativistic stuff in the universe, is something that is qualitatively different from ordinary matter, from baryonic matter. And there's also conclusive evidence that the large majority of this dark matter is a new elementary particle. So this is a good point in time to ask ourselves, well, if we have evidence for a new elementary particle, what are we looking for? What is an elementary particle? And imagine that you're going on a date and you tell your date, well, I'm an elementary particle physicist. And your date goes, well, what do you do? What is an elementary particle? And at that point, there's one way to have that date transform into a complete disaster, which is, as is often the case, is to tell the truth. And the truth is that an elementary particle is an irreducible unitary representation of the Poincare group. So this is the technical definition of what an elementary particle is. It's also a mouthful, but it's a useful mouthful because there is a theorem due to Eugen Wigner that assures us that all such representations are labeled by two numbers. One real number is the mass of the particle, and the other is the spin, which is an integer or half integer number. So any new elementary particle will be labeled in this way. And so it makes sense to ask, well, when it comes to this new elementary particle that we call the dark matter, what do we know about its mass and its spin? Well, the first thing we know is that an elementary particle's quantum effects must not get in the way of gravitational collapse. And what that means is that the de Broglie wavelength of the dark matter as a particle cannot exceed or be comparable to the size of the smallest structures in the universe that we observe as gravitationally collapsed. These structures are dwarf galaxies. And so the requirement, since dwarf galaxies are roughly in size a kiloparsec or so, is that the de Broglie wavelength of the dark matter as a particle be smaller than 1 kiloparsec. Now, if you put in the numbers and reminding yourself that 1 kiloparsec is 3 times 10 to the 21 centimeters, you get, using the appropriate velocity dispersion for these systems, that the mass of the dark matter is bounded from below by roughly 10 to the negative 22 electron volts. That's a very, very small number. And in fact, it's so small that obviously it only applies if the spin of the particle is integer. If the particle is a boson, of course, if it were a fermion, you would have much stronger limits from Fermi-Blockian type arguments. But this is a very general lower limit on the dark matter mass. What happens at the other extreme? How massive can a point-like new constituent that could be the dark matter without violating observations? Well, in this case, the relevant observations are structures such as globular clusters or these galaxies, which are very stable and very old. You would imagine that if a massive point particle passed through these systems, it would gravitationally disrupt them. In fact, it would tidally disrupt them in ways that look nothing like observations. And if you put in the numbers, in this case, you get an absolute upper limit, which is in the order of a few solar masses. That translated into the same units as before is 10 to the 67 electron volts. And if you're curious about a recent update on this, I point you towards my paper with my collaborator Julia Cullen and Nolan Smith on this very same topic. So what we're presented with when it comes to dark matter as a new constituent is a huge landscape of possibilities, where the mass of the new particle ranges from below 10 to the negative 20 to north of 10 to the 70 or 70 or so, which means that we have a landscape of over 90 orders of magnitude that could be filled with any suitable candidate for the dark matter as far as observations are concerned. Now, within this landscape, the community has had a love affair. And this love affair centered on a specific range of masses around the electroweak scale for very good reasons, both theoretical and experimental. We've set out a huge program of directly detecting this dark matter, as well as other techniques that revolve around the assumption that the dark matter is an electroweak object. But when it comes to putting these efforts on the right scale, you see that really we are looking under the lamppost of a large swath of possibilities. In particular, across this landscape, it is not technically correct to talk about elementary particles throughout. And the reason is that at some scale, called the Planck scale, point objects are no longer to be identified as particles. So let me tell you a little bit how I think about the Planck scale. So the Planck scale is, of course, defined as the mass scale that in natural units corresponds to the gravitational constant of newtons. Now, physically, what the Planck scale represents is the scale at which the Schwarzschild radius of an entity of mass m, which grows linearly with the mass of the entity, equals the Compton wavelength, so the inverse mass in natural units, of that same entity. And of course, the Compton wavelength scales inversely with mass, and therefore at some point, these two quantities will meet, and they meet exactly at the Planck scale. So what that means physically is that for masses below the Planck scale, we don't really talk about black holes, right? We don't talk about the electron as a black hole because its quantum properties are much more significant, are much larger in size than its general relativistic properties. But similarly, if the mass of an object is beyond the Planck scale, vice versa, the Schwarzschild radius is much larger than the Compton wavelength, and the quantum properties of the object are in some sense swallowed by its general relativistic properties. And so we really ought to talk about these objects, trans-Planckian objects, as fundamentally black holes. So today, we will talk about black holes in relation to the question of what is the dark matter. Interestingly, black holes, as you know, from general relativistic theorems, are also labeled by the same numbers, the mass and the spin. And except in some exotic formulations of quantum gravity, the spin in this case is a classical quantity, so it's not quantized. But it will not really play a crucial role for us today. So what comes next in my talk is really a journey that will take you all the way from the Planck scale up to stellar masses, ranging and covering anything from stellar masses to asteroid mass, to Everest mass objects, to whale mass. Whales are very dear to my heart because here on the western coast of the United States, we have many, many resident whales, are my friends. Down to grain of salt candidates. The Planck scale is a macroscopic scale that weighs as much as a grain of salt or a few micrograms, which is fascinating. Of course, the size in terms of length scales or time scales, the Planck scale is the smallest that we can legitimately think of as making up our space-time. but the corresponding mass is a macroscopic one. So let's take away this journey. But before we get there, let me make a qualifier. Today, I will not talk about how these black hole candidates as dark matter, which obviously are non-stellar. They are non-stellar because stellar black holes are a small fraction of the endpoint of stars, which in themselves are a small fraction of the endpoint of baryons, which in themselves, as I said at the beginning, are a small fraction of the dark matter. So stellar black holes technically are today dark matter, but they're very, very tiny, probably on the level of sub 10 to the negative 6 of the dark matter. So where did these non-stellar black holes come from? Well, there's a whole lecture series that I could give about this. There's many, many possibilities that relate to how black holes could form in the very early universe or in the relatively late universe. Unfortunately, again, today I will not have time to talk about this. It is important to understand that the key mechanism is the same as for stellar black holes. So you have an overdensity, which of course in the early universe is much easier to accomplish than in the late universe, of matter or radiation, and you collapse that overdensity into a black hole. The origin of the overdensity, again, can stem from a variety of physical processes. And of course, also as a result, different formation mechanisms for these non-stellar black holes will lead to a different imprint on the mass of these objects. And so given a particular formation scenario or formation avenue, you will have a different range of masses, which again will cover the whole range that I mentioned below or earlier, from grain of salt to stellar mass. Now, for many years, people relied on pictures for primordial or non-stellar black holes as dark matter that looked like this. So this plot represents as a function of the mass in solar masses of non-stellar black holes, the fraction of the dark matter that could be in black holes. Anything that is shaded in this plot is ruled out. So looking at this plot, when I was in graduate school, people would say, well, evidently only a small fraction of dark matter could possibly be in black hole because of all these constraints. Now, this picture was, over the last few years, shown to be incorrect. And the correct picture is one where there's a large swath of masses that I will be talking about today, where, in fact, black holes can be 100% of the dark matter. We know that for sure. And there are other ranges of masses that accommodate a large fraction of the dark matter. And I'm happy to talk about what went wrong with those previous constraints. But again, I don't have time to go into the details today. Good. So let's take it away. And we're going to start our journey from the more massive black holes, closer to stellar mass black holes. These are the guys that actually triggered me as a scientist who's devoted several decades of his scientific life to dark matter as a particle. So, what has always bothered me is the notion that it's really hard when you see a signal that could be attributed to dark matter to tell whether the signal is really uniquely associated to the dark matter or not, or it's instead an astrophysical artifact or a background. So in this business of black holes as dark matter, I was comforted by realizing that in fact there is an unmistakable signature of primordial black holes as dark matter when these objects have a mass below the minimal mass that they are required to form black holes if they are stars. Okay, such minimal mass is known as the TOV, the Tolman-Oppenheimer-Volkoff mass, and it's essentially a generalization of the Chandrasekhar mass in the relativistic limit. So any merger that gravitational wave experiments observe that involves two black holes, if one of these black holes is subsolar mass, for sure, that object has a primordial origin. And of course, there's some qualifiers because there may be other exotica that could have a point-like or almost point-like nature, and they're not black holes, but that's a different story. If you're interested, I have a recent paper on this. The key point is that there may be many, many such events with current generation gravitational wave experiments. We've calculated that, in fact, as a function of the fraction of these objects as dark matter and of the fraction of these objects that are light enough to be subsolar, but massive enough to be detectable at LIGO, Virgo, Cagra, you can have as many as tens of events every year. Now, of course, gravitational wave collaborations have indeed looked for these events. There's no officially confirmed events. However, there are events that independent researchers have found with admittedly low confidence that involve a subsolar mass object. One example is shown here. Notice that this actually has a significant posterior probability for one of the two masses to be well below one solar mass. This was independently discovered by a Spanish group by Gonzalo Moraz et al. You may want to notice from the time print of this event that it's associated with April 1st. So hopefully it's not an April Fool's joke. So that's the first evidence. Another evidence came a few years later, again, I believe from a Spanish team that calculated that in this event, actually, there should be, or at least, again, the posterior indicates two subsolar mass objects. Unfortunately, false alarm rate for this type of event is relatively high, is 1 in 5 years. But, the point is, these events may exist, and I suggest that we all as a community stay tuned, because evidence for the existence, if not for the abundance of primordial black holes as dark matter, could very well come soon from gravitational wave experiments. Now, let me focus on the asteroid mass range. As I claim, this can be 100% of the dark matter. The bad news is that these events are that these candidates are very hard to constrain. Microlensing, which is a prime technique to go after these objects, has serious limitations that people have, including me and my team, realized over recent years, which begs the question, how can we detect these admittedly very compelling dark matter candidates? The main idea of microlensing is a very well-known one. It hinges on the property of general relativity that light travels along geodesics and that mass bends spacetime in ways that lead to the amplification of a light source in the background of an observer. So if mass transits in between the light source and the observer sees for a temporary limited amount of time an amplification of the source. Now, the best constraints that have been obtained in this business have been gathered by a relatively short, a few hours long observation of our sister galaxy M31, the Andromeda Galaxy, with this wonderful piece of equipment known as the Subaru Hyper Supreme camera. And I've worked with my collaborators to understand exactly what has been done to constrain asteroid mass and to search for asteroid mass black holes with this technique. Now, the main problem that we found with the original limits that were set by those observations is one that has to do with the assumption of the size of the stars monitored in Andromeda. First of all, let me draw your attention to the fact that these observations managed to monitor individual stars, and as many as several millions individual stars in Andromeda, which is a mind-bending fact in at least the simple mind of a theorist. However, the problem is that the constraints that were derived all assumed that the stars had the same size as the sun. That assumption was fundamentally incorrect. Using population models for the stars in Andromeda, we convinced ourselves that, in fact, stellar objects of the size of the sun were a very, very small fraction of all of the stars that the Subaru camera could monitor in Andromeda. Everything else was significantly larger, as you can see here. We range from a few solar masses all the way up to almost 20 solar masses. So what does this imply? Well, this implies that one cannot neglect finite source size effects. And that's a key fact that actually also informs searches for very small black holes through a technique known as femtolensing, but this would take us afar. So let me tell you what these finite source size effects boil down to be. So again, you have an observer, you've got a light source, and you've got a black hole, probably a smaller black hole than M87 star, that passes through and amplifies the light of the source. However, if the source is extended, as you can see from these schematics, the light that gets bent and gets to you as amplified would already get to you, right? Without the need of a gravitational lens. Now, that's a problem because when you actually do this exercise properly, you essentially flatten out the magnification of the source very significantly. In fact, in this instance, you see that the amplification is halved. The condition for this is that technically the Einstein radius of the lens must be smaller than the angular size of the source, which in the case of the Andromeda constraints was a very common occurrence. And so this is in part why the constraints that were set were in fact significantly weaker once we accounted for the finite size source effects. And so again, this window is apparently completely legitimate to think about asteroid mass black holes as dark matter candidates. Now, it's fascinating to note that microlensing events have been observed and that indeed finite size source effects are present in the observed events. The problem is that these events are most likely not what we're looking for. The problem is backgrounds, unfortunately. And again, in this case, background stems from so-called freely floating planets, which are nothing but planets that have been ejected in one way or another from their host planetary systems, and they float around in the galaxy, very sad, cold worlds that travel afar from stars, and they roam the galaxy in incredibly large numbers. Now, luckily for us, there is a telescope that is slated to be launched soon, in fact, in a couple of years, the Nancy Grace Roman Space Telescope, that will monitor the center of the galaxy, the galactic bulge at large, and is slated to find hundreds and hundreds of microlensing events. Most of these are anticipated to be from freely floating planets. And so the key question is, will we be able to distinguish freely floating planets from black holes? And the answer is maybe. We ran a statistical simulation of these events at Roman. We wrote a code that is publicly available with which you can carry out these simulations. And for instance, one of the things you can do is to make histograms of the event duration of these microlensing events. And you will find that in many cases, these histograms are sort of double peaked. And if that's the case, it is relatively easy to distinguish statistically in a rigorous way the existence of a second population in addition to freely floating planets. However, that's not guaranteed, as shown here on the right. For some choices of masses and abundance, unfortunately, asteroid mass black holes will not be distinguishable from freely floating planets, which begs the question of how tight and how deep the discovery potential of Roman is in the same plane that we looked at before. Please notice that these are more massive black holes than the ones that can be 100% of the dark matter. And so we have a lot of work to do. And the work revolves around the question of how we can access observationally deep inside the asteroid mass window for primordial black holes. One possibility is that these objects at formation produce gravitational waves. This is a very concrete possibility that emerges in many formation mechanisms. On the other hand, it's not a guaranteed possibility. It's model dependent. There are many formation scenarios that avoid the production of gravitational waves. Now, the other possibility, since the limitations of optical surveys come from the wavelength of the light that you're using, And essentially, the idea is that the physical size, the Schwarzschild radius of asteroid mass black holes is much, much smaller than the wavelength of light. And so, if anything, diffraction doesn't allow you to see really gravitational lensing or anything related to black holes this small. So you may say, well, let's just use shorter wavelengths, higher frequencies. But the problem is that these higher frequency sources are very scarce, and it's very hard to monitor a large number of them. So that is a possibility, but not a robust one to set constraints. So what we've been working on is instead to use the same techniques as LIGO does to detect black hole mergers. Now, the problem here is that the frequency of gravitational waves emitted by a black hole merger depends on the physical size of the black holes that merge. In fact, the frequency is the inverse size is roughly 1 over the crossing time of the black hole. And so in the case of asteroid mass black holes, that frequency goes all the way up to gigahertz. Now that seems to be damning because we have no idea how to detect gigahertz gravitational waves at present. In fact, that's not entirely true because there are apparata like ADMX, which is, of course, a resonant cavity designed to detect axions, that may be repurposed instead of detecting axions to detect gravitons. This is an interesting technique. And again, I don't have time to describe this in detail. It revolves around a process known as Gerstenstein effect, where essentially, if you write the electromagnetic Lagrangian in the background of linear gravity, you get a term that couples H, the leading order perturbation to flat spacetime, to electromagnetism. And so you have the concrete possibility of detecting.
What kind of justification with all of the speculation?
I believe somebody must be muted, to detecting these high frequency gravitational waves. Now, a new technique that my postdocs and former students have also devised is the perturbation of planetary orbits within the solar system. And I think that's a very good idea, even though it is at present untested. Now, let me tell you a little bit about black hole explosions. This is a term that Stephen Hawking came up with, and it revolves around the idea that if you consider a field theory in the background of a black hole metric, an asymptotic observer is slated to observe a thermal background field at a temperature that is given by the ratio of the Planck mass squared divided by the black hole mass. And as such, black holes radiate exactly like a black body. As a result of this, in turn, black holes evaporate away. And they evaporate away in exactly or very similar to the way in which black bodies evaporate. So it's going to be essentially a Stefan Boltzmann type relation. So the shedding of energy and mass proceeds proportionally to the area of the object times the temperature to the fourth power. Now, the area, of course, scales like the square of the Schwarzschild radius, which is proportional to mass. And so dmdt is proportional to 1 over mass squared. So you've got a runaway process where light black holes emit very, very large amounts of energy and massive black holes instead don't. This runaway process leads to, again, what Hawking called a black hole explosion. And the fact that if you have anything that is roughly lighter than 5 times 10 to the 14, so about 1 million tons, which corresponds to a temperature of about 100 MeV, according to this formula, these objects are exploding today. The fascinating thing about black hole explosions is that the light curve, in other words, the photons emitted by an exploding black hole, is absolutely universal. Is absolutely universal up to knowledge of what happens to the number of degrees of freedom as you crank up the temperature of the black hole. So once you fix the number of degrees of freedom, be it, for instance, plus SUSY or just a standard model, you fix once and for all for any black hole in the universe what happens as the black hole burns away through Hawking evaporation. And essentially what this light curve looks like is an inverse or backwards in time gamma ray burst without an afterglow, meaning that after the explosion, the products are expelled essentially radially at very large energies, and so there's no photosphere that forms at the edges of an exploding black hole, unfortunately. So what happens here is emission completely ends, is truncated for good. Now, what we've done in my group is to search for these PBH explosions, which entails looking at a diagram of where these black holes are as a function of how massive the black holes are in whatever units you choose at the time of observation. So of course the mass tells you about the remaining lifetime as well as the temperature. So different observatories will be best suited to look for black hole explosions depending on the mass of the object that is exploding. The sensitivity of different observatories as a function of distance and mass is shown here. So the best bet you have for objects that are exploding right now and they're towards the end of their explosion phase is with Cherenkov telescopes, such as CTA, Veritas, or LASSO, etc. Now, if you're looking for objects that are evaporating but very slowly, then the best bet you have is either the Large Area Telescope on board the Fermi Space Telescope or gamma ray burst monitors. In either case, the question is, have we observed any such objects? And you can rephrase this question as, have we cataloged any of the variable sources in ways that can be conducive to identifying them as exploding black holes? We claimed that, in fact, there are several such sources that the LAT may have identified. Unfortunately, the distance to such sources is or has to be inferred as very, very nearby, meaning, on the order of an astronomical unit. What that means is that we predict over the time of observation of these sources a significant proper motion in the sky. However, for any of these sources, no proper motion was observed. And so what these, variable sources are probably, or most likely, unassociated, very, very distant sources that are changing with time, such as AGN, that are evolving, but they're not nearby events. So that's too bad. You can ask the same question for GRBs, and in fact, we are perfecting an early search that we've done around short duration GRBs. Now, the good news is that there are ways in which you can tell whether a GRB type event is nearby or not. That relies on the fact that we have a whole slew of GRB telescopes around Earth. And so these telescopes, which are very good at timing resolution, can actually tell you whether an event is local or if it's asymptotically far away. And so we are using this interplanetary GRB monitors network known as IPN to look for events which are not GRB, but rather nearby exploding black holes. So stay tuned. Now, even if a black hole is completely exploded, and let me skip this in the interest of time, even if black holes have completely exploded, sorry about this, you can still get something that is related to dark matter and or that informs cosmology in various ways. For instance, in my team, we've shown that dark matter production can be associated with evaporation of black holes. And in fact, not only that, but also the production of a baryon asymmetry. We've shown, for instance, that a minimal addition to the Lagrangian of gravity that encompasses a Kretschmann scalar coupling to the B minus cell current can produce baryogenesis and dark matter during black hole evaporation. Also, high-frequency gravitational waves are slated to be produced if black holes have exploded in the early universe and in principle are observable, as we've shown in a couple of recent papers. So please ask me if you're interested in this. Now, let me spend the last part of my talk on grain of salt black holes. What are these? These are remnants of evaporation. We don't really know what happens at the Planck scale. That's the realm of quantum gravity. We don't know what the right theory of quantum gravity is. But what may happen is that quantum gravity doesn't allow for Hawking evaporation to continue. And if Hawking evaporation stops at the Planck scale, then one is stuck with, number one, a relic, and number two, most likely a relic charge, a relic electric charge, because, of course, shedding of charge from an evaporating black hole is a stochastic process, and generally you're left over with some relic electric charge. Now, this charge may very well disappear. There are many instances, sorry for the interference of my cat, may in fact be shed away, for instance, by Schwinger pair discharge. But again, we are close to the Planck scale, and so it's unclear whether Schwinger pair discharge works or not at that scale. Now, if this population of charged Planck scale relic in fact exists, the good news is that we can use direct detection experiments such as xenon 1 or neutrino experiments to detect these charged relics. In fact, we realized that the best bet is to use something called paleodetectors that actually our next speaker is an expert on. Paleodetectors are essentially very pristine crystals that have lived most of their lives deep underground. They're uncontaminated, and searching for a defect in these otherwise pristine crystals may be indicative of the passage of a massive charge relic. So let me wrap up here. I've taken you on a journey that started with stellar mass black holes. It's very fascinating to think that we can identify a primordial black hole with gravitational wave experiments. Asteroid mass black holes are really an interesting spot to look for dark matter, but one that we require some work to really search deep into this window. Exploding black holes are fascinating. We may, in fact, have a chance at detecting them directly and use them to detect the presence of otherwise completely dark degrees of freedom by studying the light curve. Exploded black holes can by themselves seed the dark matter and even the baryon asymmetry and produce gravitational waves. And finally, grain of salt black holes may offer a compelling window for dark matter that may be detectable if these objects are carrying an electric charge. And let me stop here, and I'll gladly take questions before Katie's talk.
Hello, can I hear me? Can you
Yes, I
hear
can,
me?
Gautam. Please go ahead.
Yeah. Hi, Stefano. Thank you for your nice talk.
Thank
I
you.
have some basic question.
Please.
One question is, what do you mean by basically the macroscopic quantum effect and the macroscopic gravitational effect, and how, in theoretical perspective, how could you explain macroscopic quantum effect and macroscopic gravitational effect in a single theory? What is your basically the assumption behind this single theory?
Sorry, Gautam, can you just repeat what you mean? So you're focusing on remnants of evaporation. Do I understand correctly?
No, I am just focusing on your first 2 or 3 slides,
Yes.
where you can explain that macroscopic quantum effect and macroscopic gravitational effect, right?
Right.
Yeah. So my question is, in the theoretical perspective, how could you explain macroscopic quantum effect and macroscopic gravitational effect in a single theory?
Yes, Gautam, very good question. I don't have such a theory. Such a theory would be quantum gravity. There has been remarkable progress in this realm that comes, for instance, by embedding notions that derive from string theory. And there is, in fact, evidence that of two things. One is that most likely Hawking evaporation works very differently when you tackle physics near the Planck scale. Now, progress on this is limited to a few decades above the Planck scale. So even string theoretic approaches don't really inform us of what happens ultimately close to the Planck scale, but it tells us something. One thing is that Hawking evaporation works differently from the semi-classical approximation that we use to treat more massive black holes, where it is legitimate to put a quantum field theory in the background of black hole. So that's number one. It works differently. We don't know exactly what happens near the Planck scale, but we do know that a couple of decades north of the Planck scale, evaporation works qualitatively differently. The second thing is that most likely Schwinger pair is not shut off by quantum gravity effects. And in fact, I've written a paper on this that qualifies how you may preserve charge on black holes. So as far as we know from models of quantum gravity, evaporation works differently, and most likely in the simplest incarnation, electric charge is lost. Anything else is in the realm of speculation, and I don't think anybody can, with a straight face, tell you what happens around the Planck scale when it comes to Hawking evaporation.
Okay, thank you. And one comment is that I think in your work somehow lambda n, that means the Compton wavelength is equal to the something of 2 pi rs, and in Schwarzschild radius is comparable to that. Is the some type of quantum gravity is behind your work? I think it may be. I don't know.
Well, my argument for what defines, which is not mine, it's a classical argument, just relies on the observation that the Planck scale corresponds to the scale when that crossing happens. There's no quantum gravity statement about that. It's just identifying a scale with the scale where there is a crossover between general relativistic effects and quantum effects.
Thank you.
Okay.